Hello students, this is Halverson, and I'm going to be doing notes on Newton's Laws. That would be chapter 5 of our textbook. So I'm going to start at the beginning and introduce them. So we're going to start with Newton's first law, the law of inertia. Just taking a look at what my notes say, if you've got an object that is just sitting there, and we say it's at rest, it's not going to go anywhere. It'll just stay put unless a force pushes it. Once a force pushes it, okay, now it starts to move. Another aspect of this law is that if the object is moving, it will keep moving in the same way unless a force comes along to maybe speed it up or slow it down. So those two things put together are called Newton's first law, the law of inertia. Now actually Galileo is the one who came up with this law. It would actually make more sense if we called it Galileo's law of inertia, but anyway, that's the way it is. We call it Newton's first law. So yeah, a ball, like a bowling ball, is a good example. It'll keep rolling a long time because it has inertia. The ball eventually is going to stop, though, because of friction. Okay, now when we talk about an object and its inertia and so on, and a force that's speeding it up or slowing it down or making it turn, what matters here is what we call the net force. So all objects actually feel many different forces, but if you add up all of the individual forces, then you come up with the net force. So for example, I have here a force, maybe it's a bowling ball or something, and it feels a downward force of 5 newtons and an upward force of 5 newtons. Now obviously those two forces are going to cancel out. So there's no net force in the up and down sense. But in my example here, I've got 10 newtons of force to the right and also 2 newtons of force to the left. When you combine those, you're going to get 8 newtons of force to the right. And so what we write is that it has 8 newtons, and then we can use the I hat vector, or in our book would use the x hat vector, and so to describe it. By the way, I'm noticing there's a little mistake here. This being a vector, it needs to have a vector sign above it. The Greek letter sigma stands for summation. So when you see something like this, a summation symbol, the little I here, it means index. And so what this is saying is that we have many individual forces. So we could have like force 1, I would be 1, plus force 2, I would be 2, plus force 3. When you add up all the different forces, like in this case there are 4 different forces, this could be force 1, force 2, force 3, force 4. When you add them all up, then you've got your answer, which was 8 newtons in the to the right. Okay, so all right, so let's keep going. Let's move down here. All right, now let's get to Newton's second law. This law kind of has 2 parts. I call them part A and part B. So the first part of Newton's second law is that if you've got an object being pushed, it's going to accelerate, and the acceleration is proportional to the net force. So my example here, I've got a wagon full of popsicles and it accelerates. Okay, now that's because I'm pushing it. Now if I push twice as hard, it will accelerate twice as much. So proportional means just that. If I pushed 3 times as hard, it would accelerate 3 times as much, and so on. There's a second part, part B. The acceleration is also proportional to the inverse of the mass. Inverse means the reciprocal. So in this case, I can continue my example. If I had the wagon of popsicles and it accelerated at a certain rate, if I were to double the mass of popsicles, double the mass of the object, then the acceleration would be 1/2 as much. Now we put the two halves together to make a kind of overall second law. The acceleration is proportional to the force divided by the mass. So that the force part of it is the first part A of the law, and 1 over the mass is part B of the law. And finally, the metric system that we use is set up, I mean, it's not really a miracle, but it's set up such that if you use a force in newtons and mass in kilograms, then the acceleration will be in meters per second squared. So it was all set up that way on purpose. Which brings us to the units here. Okay, so I already said it. Newtons is our unit of force. Kilograms is our unit of mass. And so here we are. Acceleration is force over mass. Force in newtons divided by mass in kilograms. So, okay, so consequently, you know, thanks to this, the way this is set up, we know that acceleration, which we already learned has units of meters per second squared, we could say acceleration has units of newtons over kilograms. And in fact, that's true. Newtons over kilograms is the same thing as meters per second squared. They're equivalent. All right, so that's units. Now, I wrote Newton's second law this way, right here. A equals F over m, and actually this is the way you're going to use it most of the time, but in most textbooks and in popular write-ups, this is the version you're going to see. You're going to see F equals ma. So you're going to see that one a lot. All right. Now, I need to mention that acceleration has a direction, right? You could be accelerating to the left or to the right or up or down. So it has a direction. So acceleration is a vector. Mass is a scalar. A scalar times a vector is another vector. And sure enough, force is a vector, right? The force could be to the right. The force could be up or down. So it's a vector. Okay. So let's see. I'm keeping an eye here on my timer. I don't want to make this video too long. All right, so let's do some examples here. I've got a giant squid, and squids have a funny kind of water rocket device. It's called a siphon, and this particular squid is accelerating at 15 meters per second. What is the thrust of the jet? What force does that rocket make it? What force does the rocket provide? So we have a given here, the 400 kilograms for the mass. We have the acceleration, 15 meters per second squared. So we can use F equals ma, we have 400 kilograms times 15 meters per second squared. Multiply, and you get the answer in kilograms meters per second squared. And these units are equivalent to, these units here, kilogram meters per second squared, are equivalent to newtons. Voila. Okay, so let's keep going. So in this example, we're finding the force. So the next one's going to be finding the acceleration, and I think my last one will be finding the mass. Okay, so here's an acceleration, finding the acceleration type problem. Okay, so we've all seen these really powerful cars, the Teslas, but they're heavy. They're way heavier than ordinary cars. This would be 2.1 tons, and they're really heavy because of all the batteries that they have to, lug around. So, now the good thing though is that those batteries have a tremendous amount of energy in them, and so the motors can provide a tremendous amount of force. 23,520 newtons of force. So, okay, what's the acceleration of the car? So we know the force is 23,520 newtons. We know the mass is 2,100 kilograms. We divide, we get an answer in newtons per kilogram, which is the same thing as meters per second squared. 11.2 meters per second squared. Now, this is a crazy acceleration. I mean, it's a lot of acceleration. It's more acceleration than the acceleration you get from just falling, right? If you fall, you're going to accelerate at 9.8 meters per second squared. The car can accelerate this much. So the ratio of the acceleration to what you would experience falling, that ratio is called the number of G's. And so the number of G's is 1.14. Which means that if you, let's say you weighed 100 pounds, when that car is accelerating, you would feel your weight downward, which is 100 pounds, but also you'd feel 114 pounds of what feels like force pushing you back into the back of the seat. So that force that you'd feel being pushed into the seat, that's called a G force. Right. Okay, last example. Now this one's finding the mass, and in this example I'm also introducing the idea that gravity being an acceleration, right? When you are falling, you're accelerating. So Newton's second law can be used in this case to relate the mass and the downward pull of gravity. And that downward pull is called the weight. Okay, so, all right, let's see. What is the weight of a 275 kilogram sumo wrestler? Okay, so here's how we do it. The downward pull of gravity is mass times gravity. Right, so this formula here, let's go with green. This formula here is a variation on the formula F equals ma. It's just that here we're figuring out the downward force from gravity, and we can use the acceleration of gravity here to figure that out. Okay. Anyhow, you plug in the 275, the 9.8 meters per second squared, and you get the answer. And so the weight of the sumo wrestler is 2,695 newtons in the downward direction. Now, I like to use F sub G to mean the force of gravity, which means the weight. However, our book likes to use the letter W, W for weight. I mean, that's okay. The only thing about using the W, though, that I don't like is that later on, W gets used for other things. Like, for example, W stands for watts, a measure of power, and so on. So there are some issues with using W. I like F sub G better. Okay. All right. So I'm going to wrap things up soon. Here, let's look at my diagram here. So this diagram kind of maps out all the possible problems you might encounter in our textbook and our quizzes and our tests. So they're all going to be force problems. And force problems can kind of break down into two broad categories. There is the category where the net force is zero. All the forces cancel out. And these are called equilibrium problems. The other kind is where the net forces don't cancel out, and these are not equilibrium problems. Okay, going back to the equilibrium problems. These equilibrium problems subdivide into static problems where nothing is moving. So like figuring out the forces on a ladder leaning against a building. That's a static problem because nothing's moving. And then there's dynamic equilibrium problems like a ball or something sinking through a viscous liquid. In my example here, a steel ball drifting down in a jar of honey. So it's going at a constant velocity. It's not speeding up. It's not slowing down. The net force is zero in this situation. Okay, and then the last kind, back to non-equilibrium problems where the net force is not zero. Your object will be accelerating, right, because the net force is not zero. So as an example, let's say I dropped a piano off out of an airplane or a helicopter. Well, that piano is definitely going to be accelerating downward. It's going to fall faster, 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 faster. That's a non-equilibrium problem. Okay, so I'm going to stop here and then pick up in the next video. All right, thank you.